Good morning, majors. So today's Unit 6, Day 3 notes, and I just want you to take a minute and go through the last 2 days and fill in this summary, which is the laws of probability. So pause your video, go ahead and fill it in. All right, guys, here it is. So I hope we filled this out correctly. For all events A and B, addition law of probability of A union B, remember that's all of A plus all of B, but we counted the middle twice, so we've got to subtract the intersection, probability of A intersecting B. For conditional probability, if we want the probability of A given B, the formula is the probability of A intersecting B divided by the probability of the second one, which in this case is B. This is just the corollary to that. Mutually exclusive events are when our Venn diagrams are completely separate. There's no overlap. So the probability of A intersecting B is 0. They're not touching. We have this formula also. The probability of A union B is just A plus B. Independent events, if they are independent of one another, then they do not affect each other. So the probability of A given B is just the probability of A. If you want the probability of B, then that's just the probability of B. If you want the intersection of probability of A and B, then we need to multiply the probability of A times the probability of B. So let's go over a couple of examples. This is going to be a lot of review, and then we'll go over something new today. So the probability of A is 1/2, B is 1/3. The union is P. Find P if A and B are mutually exclusive. So mutually exclusive, they don't have any overlap. And if the union is P, this is just going to be 1/2 is probability of A, and 1/3 is the probability of B. So the probability of A union B is the probability of A 1/2 plus B, which is 1/3. And I think if you get a common denominator, we will get, or put it in your calculator, make it a fraction, 5/6. If they are independent events and we want the A union B, so remember, for all events, to find the union, we can do the probability of A plus the probability of B minus the intersection. But specifically, we are asked about find A union B if A and B are independent. So this is how we're going to find the intersection. So probability of A is 1/2 plus the probability of B is 1/3. We already know this one, 5/6. Minus the intersection. The intersection of A and B is the probability of A times the probability of B. So 1/2 times 1/3. And this is 1/6. We already know that this is 5/6 minus 1/6 is 4/6, but we need to simplify this to 2/3, 2/3. And that's going to be our answer. You guys can try this one. Let's try number 3. If the probability of X is 0.5 and the probability of Y is 0.7, X and Y are independent events. This is very important. Determine the probability of the occurrence of both X and Y. So given that they're independent events, I went up here and I wrote the formula. Independent events, we have an intersection, or the intersection N is probability of A times probability of B. We just wrote it down because we're probably going to need that. So both X and Y, that means the intersection of X and Y. So the probability of X and Y equals the probability of X times the probability of Y. I think this is 0.35. You can multiply them. Just a lot of dots going on. Maybe we can use parentheses instead. Alrighty, the probability of X or Y is the probability of X or Y, which is the probability of X plus the probability of Y minus the intersection. The probability of x is 0.5. The probability of y is 0.7 minus the intersection, which is this formula. We have a special formula for that. We multiply them together, which is 0.35. And I think that we get something like 0.85. Try it out and make sure. Make sure I'm right. The probability of x nor y is the same as the probability of x or y. We don't want either, but so the complement of that. And this is 1 minus x or y. Well, x or y we have right here. So 1 minus 0.85, which I think is 0.15. 0.15. Okay. X but not y. Well, these are independent events. So we want the probability of x intersecting not y. So the complement of y. Well, so the probability of x intersecting the complement of y, remember for these independent events we multiply. So the probability of x times the probability, ooh, what happened? Sorry, of x times the probability of y complement. Well, y is 0.7, so the y complement is going to be 3.3, 1 minus 0.7. So this is 0.3 times the probability of x, which is 0.5, and this becomes 0.15. The probability of x given that y occurs, remember if they're independent events, x given that y occurs is just x. So this is just the probability of, let me write it down, x given y is just the probability of x, which we know is 0.5 in this case right here. Alrighty guys, go ahead and flip that paper over. This is what we would say is an independent event. A fair coin is flipped and a fair six-sided die is tossed. One does not have to do with another. What is the probability that the coin lands heads or the die rolls a 6? So these are independent events. So the probability of heads or is a union, a 6, right, is the probability of heads plus the probability, the or means this one plus this one minus the intersection. So the probability of a 6 minus the probability of the intersection, H intersecting 6, or when they're independent events, it's just the probability of H times the probability of 6. So the probability of a heads, or as opposed to a tails, there's only 2, so that's 1 over 2. The probability of rolling a 6 is just 1 over 6 minus the probability of 1/2 times 1/6. I believe if you use your calculator, you get 7 over 12. Check it and see. Alrighty. Oh, let's do this tree diagram. So it says the following probabilities were found for 2 events R and S. So the probability of R is 1/3. That means that the probability of S is going to be 2/3, or not R, is 2/3. The probability of S given R is 4 over 5. So the probability of S, given that R happened, so R happened and then S is 4 over 5. So this is 4 over 5. That means that this one has to be 1 over 5. It has to be 1, equal to 1. If this probability of not R happens, or the probability of S given not R happened is 1/4, then this one has to be equal to 3/4. Now we can probably fill these in. Find the following probabilities. The probability of R intersecting S. Remember, this is going to be, I can use this formula right here. So the probability of S given R, I just wrote it down from the page before, is the intersection over the probability of the second one, which is R. So the intersection is the one we don't know. We can actually solve for the intersection by maybe like cross multiplying. And so the probability of R intersecting S is the probability of R, which we have 1/3, times the probability of S given R, which is 4 over 5, which is equal to 4 over 15. Alrighty. I think these are ones you can do. Remember, we have a formula for that, and you're going to have to use this. Now, I want to go over, these are going to be a little bit new. Discrete random variable. A random variable represents in number form for the possible outcomes which could occur for some random experiment. So, represents in number form the possible outcomes a discrete random variable. A discrete random variable X has these possible values. For example, the number of binders owned by students, the number of houses in your neighborhood that might have a gas stove. A continuous random variable X has all possible values in some interval. Like heights of all men could lie between these centimeters. I don't know why they use centimeters, probably inches for us. The volume of rainwater for Reston during a given month will have this range. For each of the following, identify the random variable and give the possible values for the random variable. Indicate whether the variable is continuous or discrete. Okay, so we have discrete and continuous. Okay, so this one, to measure rainfall over a 24-hour period in Singapore, the height of water collected in the rain gauge up to 200 millimeters is used. So the height, so X is the height of rainwater. X can be between 200 and up to 200, so I guess to 0. This is going to be continuous. To study the performance of a history class, the marks out of 50 on the last unit tests are considered. So this time our variable is the number of marks, or grade, number of marks. And it's out of 50, so it could be 0, 1, 2, all the way to 50. This is a discrete. I want you guys to try the other ones. A supermarket has 3 checkout points, A, B, C. Consumer Affairs checks for accuracy of weighting. Each scales each checkout. If a weighting scale is accurate, yes, is recorded, and if not, no. Suppose the random variable is X is the number of accurate weighing scales at the supermarket. Okay. What values can X have? List the possible outcomes. 3 checkouts. So describe using X the events of their being. Since X is not the weight, is actually the number of accurate weighing scales, and there's 3 scales, then we could have 0 of them work, we could have 1 of them work, 2 of them work, or 3 of them work. And the list of possible outcomes could be something like, let's say this is A, B, C, and this is X. We could say that these 2 work and this one doesn't, or they could say none of them worked. We could say, let's go in order. Let's say like Y, no. There'd be 3 of them. None of them worked. Let's say like Y, no. This would be 2 of them worked. Y, no, Y would also be 2 of them. No, Y. I guess the rest would have to be 1s, right? Y, no would work. 1 of them would work. No, Y, no. That would also be 1. No, Y would also be 1. Okay? Describe using X events that there is 1 accurate scale. So when X equals 1, at least 1 accurate scale. At least 1. At least 1 means when X equals, or is equal to 1, 2, or 3, all 3 of them could work, all but the 0. So when X is greater than or equal to 1, that's it. So for number 3, it says that we're tossing 2 coins, and it could, when we toss them, we can either get a heads and a heads, a heads and a tails, or this one could have been a tails and this one is a heads, or we could have gotten 2 tails. I think that is the only thing that can happen. So X is the number of heads. So X could be 0 heads, 1 head, or 2 heads. So 0, 1, or 2. If it's 0, 1, or 2, the probability of getting 0 heads, since there's 4, this is going to be 1 out of 4. The probability of getting 1 head, it could have been heads and tails, or tails and then heads, but this is still just 1 heads. Well, this is 2 out of 4, or a half, simplify it. The probability of getting 2 heads is 1 out of 4. So we have either 1 out of 4 or 1/2. I should make this bigger. Oh, it's fine. 1/2. And this is the probability of getting heads. And these are heads. So if I get 0 heads, then that probability is 1/4. So this is a graph. If I get 1 heads, then that probability is 1/2. And the probability of getting 2 heads is also 1/4. Okay, shaded in maybe. All right. Probability distributions. For each random variable, there's a probability distribution, and it is between 0 and 1 inclusive, so it could be 0 or 1. So that is the probability. The summation means we're adding each time we plug in. We start at 1 and then we end at n. But when we add these all up, it has to give us 1. It can be given in 3 forms. We can make a table, we can do a probability mass density function, and or we could do a graph, which I just showed you a graph. It says it provides us with all the possible outcomes of variable and the probability of the occurrence of each variable. I am not going to try this one. I actually want to try, actually, let's just go back. Let's try it. So it says a magazine store recorded the number of magazines purchased by its customers in 1 week. 23% purchased one magazine, 38% purchased two magazines, 21 purchased 3, 13 purchased 4, 5% purchased 5. What is the random variable, the number of magazines purchased by the customer? Make a probability table for the random variable. So if this is x and this is p of x, probability of the x, it says that some purchased 1. Oh no, this is 1. 1, 2, 3, 4, and 5. So I'm going to go from 1 to 5. And the amount that purchased 1 was 38%. Or 23% purchased 1. So 0.23. 2 is 0.38. 0.21. 0.13. And 0.05. Graph the probability distribution using a spike graph. So I'm going to go from 0.1, 0.2, 0.3, 0.4. I do not think anyone was way over 0. Anyone was over 0.4. Okay. So I'm going to remember these numbers. The people who purchased 1 magazine was 0.23. So maybe like right here. The people who purchased 2 magazines was 0.38. So almost 4. Almost 4. The people who purchased 3 magazines was 0.21, so a little bit over 2. And the people who purchased 4 are, I think it was 0.13, so a little bit over 1. And then the people who purchased 5 were 0.0 something, 0.05. So that was a half this. If X is the number of magazines purchased, find the probability of X is greater than or equal to 3. So the probability that X is greater than or equal to 3 can be equal, it's inclusive, is this probability. So 0.21 plus 0.13 plus 0.05. So the probability of X is greater than or equal to 3 is 0.21 plus 0.13 plus 0.05, which is, I think, 39. Check it out and see. You guys can just plug these numbers in to find this one. It's pretty easy. This is the last problem I'm going to go over. Example 6. So a bag contains 4 red marbles and 2 blue marbles. 2 marbles are randomly selected without replacement. So this one, remember, if we don't put it back, then we're going to subtract 1. If X denotes the number of red selected, find the probability of the distribution of X. I'm going to do a tree diagram. The probability of red is 4 out of 4 plus 2 is 6. So 4 out of 6 is 2/3. So that means that the probability of blue is going to be 1/3. Gotta find a red or a blue. If we take out a marble and it is red, then we're going to have 5 left, but only 3 of them are going to be red marbles. So this is going to be 3 out of 5. And all the blue ones should still be in there, so this is still 2 out of 5. Okay. Now, if I picked a blue marble, then there's still going to be 1 taken away, but it's blue. So the red, there's the same amount, still 4 out of 5. But since we took a blue one away, there's only going to be 1 left. It says, if X denotes the number of red selected, find the probability distribution of X. So this one is the probability that it is a red and a red. And this is, remember, since we're multiplying them, this is going to be 2 times 3 is 6 over 15. I think I can simplify this to 2 over 5. The probability of red and then blue is 2 times 2 is 4 over 15. I don't know if I can simplify that. And then the probability of blue and then red, is still 1 times 4, which is 4 out of 15. And then this one is the probability of blue and then blue, which is 1 over 15. All right, I just drew a little table. I am going to let X denote the number of red selected. I have X. There is 1 time where there's no red selected. There's 2 times where there's 1 red selected, or 2 reds could have been selected. So my probability index distribution of X is when 0. This is a 1 in 15th chance that no reds will be selected. If 1 red is selected, well, there's a 4 and a 4, so that's an 8 in 15 chance that 1 red is selected. And if 2 reds are selected, that is a 2 in 5 chance. All right, guys, I want you to finish the rest and ask me if you have any questions. Have a wonderful day.